in last couple of lectures we investigated the problem what is called the array analysis. That means if the array configuration is given, if the current excitation is given on each of the array element, then we can find the radiation pattern for that array. In practice, however, the problem is opposite. A user specifies a radiation pattern and he is interested in finding out what array configuration and excitation would give that radiation pattern. This problem is called the array synthesis problem. So here the radiation pattern is specified and we have to find the parameters of the array, like the number of elements required in the array, the spacing between the elements of the array, and also the current excitation of the antenna elements of the array. Just to get an example, there may be an application where we want to have a reception of some low intensity signal, but there is a strong interfering source located somewhere in a specified direction. So while getting the reception, we would like to eliminate the radiation coming from the interfering source. The simplest way of doing that is we can place a null of the radiation pattern in the direction of the interfering source, and then that radiation coming from the interfering source will be killed. So by designing the radiation pattern appropriately, if we place a null in the direction of the interfering source, then the low intensity signal can be received effectively without modifying your receiving system. Many applications we would like to illuminate a certain zone, angular zone, for reception or for transmission, and we want that the power should not be wasted in some other direction. So we may be interested in getting a radiation pattern which looks like an angular sector. So in practice we have a variety of radiation patterns depending upon the application, and now we want to find out what would be the array configurations and the excitations which would give the flexibility of designing that radiation pattern. So today essentially we discuss the problem what is called the array synthesis problem, and this problem is not as straightforward as the array analysis problem, because in analysis the array was given, excitation was given, so we could simply apply a superposition of the fields and we can find the variation of the electric field as a function of angle and we get the radiation pattern. In this case the problem is opposite. Of course we know that there is a relationship between the radiation pattern and the current excitation, and that is there is a Fourier transform relationship between these two, but we also have seen that there is no uniqueness from coming from radiation pattern to the current distribution. There was ambiguity in that, and that is the reason the array synthesis is a rather difficult task. So in this lecture essentially we develop the theoretical basis for synthesizing a radiation pattern of an array, and then we will take some special cases of radiation patterns, like having the radiation pattern specified only by the nulls or specified by a sectoral zone or something like that. So in general, let us say we have an n element array, and now we want to use essentially all degrees of freedom. So we want to say the number of elements we can change the inter element spacing also, and we can change the current excitation also. However, in practice the inter element spacing is not varied. We keep the inter element spacing d same for the array and try to manipulate the radiation pattern only by controlling the complex current excitation on the antenna. So normally in practice the number of elements are given to you, also the inter element spacing is given to you, or the maximum size of the antenna array is given to you. From there you can find out what is the maximum inter element spacing, and then one can ask a question, what should be the current excitation for the antenna elements, so that we get the radiation pattern as close to the desired radiation pattern as possible. So let us say we have the antennas, and without losing generality, let us say we have antennas which are n plus 1 antennas. We have somewhere a element which is element of symmetry, and we have these elements which are n plus 1. And the currents are excited in such a way that the amplitude of the n plus 1th element, that is unity with 0 phase. So, without losing generality, let us say that we have n plus 1 elements, and we also say that the current excitation of n plus 1 element is unity. So, the current which you have will be I of n, that is equal to 1 angle 0. So, we excite this current element. So, let us say this element we start with 0, 1, 2, 3 and so on up to n. So, we have n plus 1 elements, and the currents in this are given by I0, I1, I2, I3 and so on up to In, where In we have chosen to be amplitude unity and the phase angle 0. Then, since the inter element spacing is constant, and since these currents are now complex, we say that the progressive phase shift which we used to talk in terms of uniform array can now be absorbed into the phase of these currents. So, we can now define the phase of the array which is psi, which is simply beta d into cosine of phi. So, again we take a direction which is the angle measured with the axis of the array, this angle is phi, and we define this quantity now, the phase psi, that is equal to beta d into cosine of phi. Recall, in case of uniform array, we had defined this quantity psi, which was beta d cos phi plus delta, which was the electrical progressive phase shift. However, that delta now we can absorb into this current excitation currents, because this I0, I1, I2, all these currents in general are complex currents. So, we also say here now in general this I0, I1 and so on are complex quantities. Once we say that, then the array factor or radiation pattern of this array, that is straightforward. The field which is produced because of the current at a very far away point will be proportional to the current here, and there will be a phase which will be corresponding to the space phase, which will be this, which is psi. So, now we can write down the array pattern for this, and let me call that as array factor AF, that is equal to magnitude of I0 plus I1 e to the power j psi plus I2 e to the power j 2 psi plus and so on till you go to In, which is equal to 1. So, this will be e to the power j n psi magnitude. Now, let us define this quantity e to the power j psi, which represent a complex number with unit amplitude. So, let us define some quantity z, that is e to the power j psi. So, that means mod of z is equal to unity. So, as the value of angle changes, the phi changes, essentially the phase of this quantity z would change. So, in complex gamma plane, this point will lie on the unit circle, because magnitude of z is equal to 1. So, the array factor can be written now in terms of this z. So, we have array factor which is I0 plus I1 z plus I2 z square plus and so on z to the power n. So, the array factor now can be represented by a polynomial of this quantity z, which is simply a phase function. The magnitude of z is equal to unity. So, there are theorems due to Shelkunov which say that a array factor can be represented by a polynomial of z, or even conversely he says every polynomial can be thought of as an array. So, now in general then we can say that the radiation pattern of an antenna for which the inter-element spacing is same can be represented by a polynomial of z. Now, as we know, the polynomial of nth degree has n roots in the complex plane. So, essentially this polynomial will have n roots in the complex plane. So, this can be written as z minus zeta 1, z minus zeta 2 and so on, z minus zeta n. So, essentially a polynomial now is represented by the product of this doublet, which is z minus zeta 1, z minus zeta 2 and so on, and zeta 1, zeta 2, zeta n are the roots of the polynomial which is represented by this. So, these are the roots of the polynomial. Now, that means at this z equal to zeta 1 or z equal to zeta 2, the array factor would go to 0. That means the radiation pattern would have a null at that location indicated by zeta 1, zeta 2 and zeta n. So, essentially the roots of this polynomial correspond to the nulls in the radiation pattern. So, zeta 1 direction corresponding to this. So, now if I take z, which is equal to e to the power j psi, that is equal to e to the power j beta d cos phi, if that is equal to zeta 1, zeta 2, zeta n, and if I invert this and find out what is the corresponding phi, that essentially indicates the direction of the nulls in the radiation pattern. So, one thing is immediately clear from here, that since this quantity is representing a phase function, that means as I change the value of phi, the magnitude of z always is equal to unity. That means this point represented by this lies on the unit circle in the complex z plane. If the magnitude of zeta 1, zeta 2 is equal to unity, then only this point will lie on the unit circle, and then there will be corresponding angle which would represent the direction of the null. So, what we see from here, that in the complex the complex z plane, you have a unit circle and zeta 1, zeta 2 will lie somewhere. It might lie somewhere here. So, this might be zeta 1, this might be zeta 2, this might be zeta 3 and so on, zeta n. Only those zetas which lie on the unit circle, they might correspond to the physical nulls. We might have an angle phi corresponding to only those zetas. When these points do not lie on the unit circle, they will not represent a corresponding value of phi, because the magnitude of this is not equal to unity, and therefore they will not represent a null in the physical space. So now, although the theorem says that every polynomial can be thought of as an array, and every array represents essentially radiation pattern and a polynomial, the root of polynomial not necessarily represents the null of the radiation pattern, because for the null to represent, the points should lie on the unit circle, and if they do not lie on the unit circle, there will not be any corresponding value of phi which will give me the null in the physical space. So though we are having a degree of polynomial which is n, we will always have nulls which are less than or equal to n. If all the nulls, all the roots lie on the unit circle, then all nulls might be visible. If some of them do not lie on the unit circle, then those nulls will not be visible in the physical space. So first thing which we can observe from here is that when a polynomial is given to you, you can find out the roots of this polynomial. You can write that this polynomial as doublets, and this will give me the location of the nulls, and if the points lie on the unit circle, then those nulls might be corresponding to the physical nulls in the radiation pattern. Why do I say might be? If the point lies on the unit circle, doesn't it necessarily mean that there will be a null in the radiation pattern? The answer is no. Let us look at this in a little more detail. Let us say we have this quantity psi which is given by beta d cosine of phi. So we have this quantity psi which is equal to beta d cosine of phi, and phi varies from 0 to pi. So the range of phi we have is greater than or equal to 0, less than or equal to pi. So that means as the phi changes from 0 to pi, the value of psi would change from beta d to minus beta d. So that means the range of psi essentially goes from beta d to minus beta d. This is the range of psi we call as the visible range of psi, because that corresponds to the visible angle, physical angle in the radiation pattern, which is phi which goes from 0 to pi. So this range from beta d to minus beta d is called the visible range of psi. Now depending upon the value of d, we may have a coverage of angle psi which might go from plus pi to minus pi, or it may go over only a portion of the total angle from minus pi to plus pi. So let us see, if let us say d we take as lambda by 4 from case 1, then the range of psi would correspond to beta d, so that will give me beta d is equal to 2 pi by lambda into lambda by 4, so that will be equal to pi by 2. So the range of psi would correspond to pi by 2 to minus pi by 2. If I take d equal to lambda by 2, that would correspond to beta d is equal to pi. So range of psi would be pi to minus pi. And if I take d greater than lambda by 2, then the range will be still larger. So if I take this d is equal to lambda, let us say, that would correspond to beta d is equal to 2 pi. So the range of psi would be 2 pi to minus 2 pi. Let us go back to the unit circle in the complex plane, and then I ask, for different values of d, what is the angular sector covered by the physical range of psi? So the point moves lies on this circle, and as I have changed the value of phi from 0 to pi, the value will change from beta d to minus beta d, passing through 0. So if I take d equal to lambda by 4, in this case, the range of psi is from pi by 2 to minus pi by 2. So I can write this circle. So if I take d is equal to lambda by 4, this would correspond to pi by 2, which is corresponds to plus beta d for d equal to lambda by 4. So this will correspond to phi equal to 0, and then the range of psi will be like that, and at this point this will be corresponding to phi equal to pi. So we got a visible range of psi from here to here. So this is the visible range of psi. That means now if I have a inter-element spacing of the array which is lambda by 4, and if the root of the polynomial lies somewhere here in this region, though the root is lying on the unit circle, still it will not represent a physical null, because the physical null corresponds to only the range of psi which lies here from plus pi by 2 to minus pi by 2. This is psi. So now for nulls to be visible in the radiation pattern, two things must happen. One, the root must lie on the unit circle. Second, the root must lie in the visible range of psi. Then and then only we can see the nulls in the radiation pattern. Any of the things not happening will not represent a null in the physical space. So in this case, we essentially can place the nulls or the roots of the polynomial in this region without significantly affecting the nulls of the radiation pattern in the physical space. So that we will investigate later when we synthesize the array which is defined only by the directions of the nulls. That time essentially this phenomena can be used more effectively. As we saw, if we take d equal to lambda by 2, then the range of psi is from plus pi to minus pi. So this is pi plus pi, this is minus pi, this is 0. So the psi essentially is going to go from plus pi all the way to minus pi. That is your range of psi. So essentially it covers all the points on the circle when d is equal to lambda by 2. If I increase the d beyond lambda by 2, then obviously the range of the psi will overlap with itself, and as we saw in the case when d is equal to lambda, the range goes from 2 pi to minus 2 pi. So here it will start with 2 pi, which is 2 pi here. It will go all the way from here up to 0, and then again it will go minus 2 pi, so it will come up to this point. So you will start with this, and the range of psi will go like that, like that. This is equal to minus 2 pi. So now if I look at these three cases here, in this case what we see is that the total unit circle is not covered by the visible range of psi. So we have a portion of the unit circle where if we put the roots of the polynomial, they do not affect the nulls of the radiation pattern. In this case, if we put nulls on the unit circle, they have directions, corresponding directions for the nulls in the radiation pattern, and which are unique. However, in this case, when I go, if I consider a null, let us say somewhere here, it would correspond to two values of psi. Let us say I take an angle, location of the nulls, let us say is this. Now this corresponds to the value of phi, which would correspond to this value of psi, which is this, but it would also correspond to this value of psi, which is here. So for a given null on the unit circle, now we have two psi values, because the visible range of psi overlaps with itself. But two different values of psi essentially correspond to two different angles in physical space, two different angles phi. What that means is, if I try to put a null corresponding to this value of psi, automatically there will be a null placed in this direction which corresponds to this value of psi. So now I do not have an independent control of every point on the radiation pattern. As soon as certain point on the radiation pattern is defined, the other point on the radiation pattern is automatically defined. So if we have a range which overlaps with itself, and that would happen if d is greater than lambda by 2, then the independent control of every point on the radiation pattern is lost. As soon as you define certain portion of the radiation pattern, the other portion of the radiation pattern is automatically defined. So looking at these three cases now, we can make the following conclusions, that in this case, since the entire range of angle psi from 0 to 2 pi is not covered by the visible range of psi, there are certain nulls which can be there in the polynomial which may not be physically visible. If I go to this, when the range of psi overlaps with itself, then we do not have independent control of every point on the radiation pattern. So the optimum inter-element spacing is d equal to lambda by 2, because in this case you cover the entire range of psi, which is from 0 to 2 pi or minus pi to plus pi, and at the same time you still have independent control of every point on radiation pattern. That is the reason invariably we prefer to use the inter-element spacing of an array which is equal to lambda by 2. So generally when we do the array synthesis, we prefer to use the inter-element spacing which is equal to lambda by 2, and then we ask the question, what would be the current excitation and the number of elements which would give the desired radiation pattern. This diagram essentially is called the circle diagram of the array, and we can essentially mark the roots of the polynomial, that means directions of the nulls, on this diagram. So this thing we call as the circle diagram of the array. So circle diagram essentially is the visualization of the roots of the polynomial on the unit circle, or in general on the complex z plane, to see whether these nulls would correspond to the physical nulls in the radiation pattern or not. Once you understand this, then synthesizing an array which is specified by their nulls is very straightforward. So as we said, there are certain applications where we would like to place the nulls in some given directions, because there is a strong interfering source coming from that direction. So if you put a null in that direction, then the interfering source will be killed. So now we can synthesize an array based on the directions of the nulls. So the simplest of this array synthesis is synthesis of array defined by its nulls. So, now the steps involved will be as follows. First, specify the directions of the nulls. Let us say they are given by phi n1, phi n2 and so on up to phi n, where n, small n represents the null and 1, 2, 3 up to capital N represent the number of nulls in the radiation pattern. Then you find out the corresponding values of size. So, you have psi corresponding to these nulls. So, psi n k, that is equal to beta d cosine of phi n k, where k would be equal to 1 to n. Then you find out the value, corresponding values of z, so which is zeta k, that will be e to the power j psi n k, and then we can write the polynomials by multiplying the doublets, which is z minus the roots of this polynomial. So, then from here you can get the array factor, which is equal to z minus zeta 1, z minus zeta 2, so on up to z minus zeta n. Expand the polynomial, and the coefficient of z give you the current excitation of the antenna array. So, get coefficients of z to the power k gives excitation of kth element. So, an array which is specified by the nulls can be synthesized in a very straightforward manner. So, first you find out the directions of the nulls which are specified by the users, which are given by phi n1, phi n2, phi n1. Find out the corresponding values of size. Find this function, the root corresponding to these values of size, which is defined by e to the power j psi n k. Multiplying by the doublets z minus the roots, you get the polynomial. Expand the polynomial, you will get now powers of z's, get the coefficients of z to the power k, that gives you the excitation of the kth element. So, the synthesis of an array which is defined by its nulls is a rather straightforward problem. Let us take a simple example to understand how do we define this. So, let us say we want to design an array which has two nulls, one corresponding to phi equal to 0, another corresponds to phi equal to pi by 2. So, I do not know how many elements will be required by this, but since there are two nulls which are specifying the radiation pattern, we require 3 elements. We require a polynomial of degree 2. So, let us say my requirement is, this is the array which is now 3 element array, I have a null in this direction and we want a null in this direction. So, this corresponds to phi equal to pi by 2, this corresponds to phi equal to 0. So, we have two nulls in the radiation pattern at phi equal to 0, at phi equal to pi by 2. Now, taking the inter-element spacing d equal to lambda by 2. So, first we choose the spacing, take d equal to lambda by 2, giving beta d cos phi equal to 2 pi upon lambda into lambda by 2 cos phi, that is equal to pi cos phi. So, we have now the size corresponding to the two nulls. So, we get here psi n1, that is equal to, when I put phi equal to 0, you will get psi n1 which is equal to pi, and you will get psi n2 that is equal to, when phi is equal to pi by 2. So, this is 0. So, this quantity will be 0. So, if I put the circle diagram for this, we have two nulls, one corresponds to psi equal to pi, and other one corresponds to psi equal to 0. So, I have one null here and I have another null here. So, this corresponds to psi is equal to 0, this corresponds to psi is equal to pi, or this angle, this point corresponds to phi equal to 0 and this corresponds to phi equal to pi by 2. Once I get this, then the roots of this polynomial which would define the radiation pattern for this would be zeta 1 will be e to the power j pi, that is equal to -1, and zeta 2 will be e to the power j 0, that will be equal to +1. So, now if I take the root which are -1 and +1, then we can essentially define now the polynomial which will be z minus this quantity, z plus this quantity, and if I expand their polynomial, that would essentially correspond to the excitation of the array elements. So, finally we can get the array factor which will be equal to mod of z minus of 1 into z minus 1. So, you get the pattern which is array factor which is equal to mod of z plus 1 into z minus 1, which after multiplying and expanding, essentially we get the coefficients which will be z square minus 1 or if I write in the way we wanted to write the polynomial in the ascending degrees of z, this will be -1 plus z square, or we can write here this is -1 plus 0 into z to the power 1 plus z to the power 2. So, the coefficient of now the z powers of z that defines the excitation of the current for the array element. So, we have these 3 elements now which are here. The inter element spacing we have taken is lambda by 2. So, this current is -1. So, here the amplitude is 1, angle is pi, that is what -1 would mean. There is no current excitation for this element. So, this element is 0. So, this current element is not there, and this will have an excitation which will be 1 angle 0. So, this will be 1 angle 0. So, essentially now we have an array. Since this current is not excited, this element is not existent. So, essentially we have an array which is this, which is having a spacing of lambda, and they are excited out of phase. So, this excitation is 1 angle pi and this excitation is 1 angle 0. So, though we initially started with a 3 element array because there were 2 nulls required, by the synthesizing this in terms of nulls, essentially we find that the 2 elements are the one which are enough to give you a null in the direction of phi equal to 0 and the direction phi equal to pi by 2. Since this is a 2 element array which we have already investigated, we can see what the radiation pattern for this would be. So, the radiation pattern for this array would be equal to, so we have got here the array for which the angle, this is phi measured from the axis of the array. So, we can get from here 1 e to the power j pi the current plus angle 1 e to the power j 0 e to the power j beta d cosine of phi. So, that is equal to -1 plus 1 e to the power j beta d cos phi, but we have beta d in this case which will be equal to 2 pi by lambda into d, which is now lambda in this case. So, d which is equal to 2 pi. So, we can write here this is e to the power j 2 pi into cos phi. As you have done earlier, we can take e to the power j pi cos phi common from here. So, this will become equal to minus e to the power minus j pi cos phi plus e to the power j pi cos phi, that multiplied by e to the power j pi cos phi. Now, since for the radiation pattern we are interested only in the amplitude variation, this term does not matter. So, essentially we get the radiation pattern which will be e to the power j pi cos phi minus e to the power minus j pi cos phi, that will be equal to 2 times j sine of pi cos phi. So, we can verify now that when phi is equal to 0, that time this quantity is 1, and we get sine of pi which is 0. So, we get a null in the direction of phi equal to 0. When the phi is equal to pi by 2, this quantity is 0. So, again sine of 0, that will give me the null in that direction. So, this is the radiation pattern now which I get corresponding to this excitation, which would have nulls in the direction of phi is equal to 0 and phi equal to pi by 2. One can also note from this direction on the circle diagram that this point essentially corresponds to psi equal to pi, which is this point, but this point also corresponds to psi equal to minus pi, and psi equal to minus pi corresponds to the angle phi which is equal to pi. So, that means as soon as we put a null here corresponding to psi equal to pi, automatically a null has been placed in the direction phi equal to pi, and which we can see from here that when we put the phi equal to pi, this quantity will become minus 1. So, again you will get sine of minus pi, that will be 0. So, you will have a null in the direction of phi equal to pi also. So, although we did not want a null, we wanted only these two nulls in the radiation pattern, automatically a null has been placed in the direction of phi equal to pi also. So, this is more like a forced null in the radiation pattern. So, we will have now 3 nulls for this array. One will be in this direction, one will be in this direction which is pi by 2, and one null which will be forced in this direction. This is the forced null which was not defined by the user, but automatically the null will come in this direction. If we did not want null to come in this direction, then we could have taken the spacing between the elements smaller than lambda by 2, and then this point will not correspond to phi equal to 0 and pi. The visible range will get shortened and the 2 points will not coincide, and then we can make sure that only one null exists in the radiation pattern. So, what we see this from this example, that now by defining the nulls of the radiation pattern, we can find out the excitation of the current elements of a uniformly spaced array where the inter-element spacing is constant, and it is possible that some of the current excitation coefficient might turn out to be 0. So, those current elements can be removed, and then the remaining element, if they are excited with the proper current excitations, then they will place the nulls in the desired direction. It is possible in this process some additional nulls also might get introduced, as we saw in this case, if the visible range of psi overlaps with itself. In this case only one point was overlapping, but in general if the d is greater than lambda by 2, then there will be more overlapping of the visible range of psi, and the more nulls will get placed other than where user want to have the nulls. Another thing to note in this analysis now is that the array pattern is defined purely by the nulls, and we do not have control over any other parameter of the radiation pattern. For example, once the nulls are defined, I now cannot say which direction the maximum radiation would be. Whatever the direction of the maximum radiation is, we have to accept that direction. So, we have control over the nulls of the radiation pattern, but we do not have control on the radiation pattern as a whole, because now I cannot control the direction of maximum radiation. I cannot control, let us say, the level of the side lobes or direction of the side lobes or so on. So, this synthesis based on the nulls of the radiation pattern is useful in practice. However, we would like to have a much better control of the radiation pattern, not only the nulls of the radiation pattern, and that is what precisely is done by what is called the general array synthesis, and that is what we will discuss in the following lecture, that if the radiation pattern as a whole was defined not only by its nulls, then what should be the current excitation to realize that radiation pattern.